Hello, everyone. We're going to start in a few seconds.
Hello, good day, everyone. Welcome to today's session of the Climate Change AI Virtual Summer School 2024. You're welcome to the day 2, which is focused on AI for agriculture, forestry, and other land use. We're so happy to have this program proudly supported by Google DeepMind, GitHub, Cepha, and Mila. Today's session, before we begin today's session, what's climate change AI? So basically, Climate Change AI is a global non-profit organization that catalyzes impactful work at the intersection of climate change and machine learning. So you can check more of our work at our website, www.climatechange.ai. You can also check our social media handles at Climate Change AI. You can also do well to follow and subscribe to us on all our social media platforms. You can also subscribe to our community platform where we share insights on community platform. You can also do well to subscribe to our newsletter as well. So a few things to note before we start. You can use the chat for general comments. I can see your comments. You're all welcome from India, from UK, from US. You're all welcome to today's session. Note that if you want to ask questions, you want to post questions directly to our lecturer, to our speaker, you can use the Q&A feature right below your screen. You can also try to upvote questions that you are most interested in. And the higher the upvote, the more attention it will be given to by our speaker. You can also click to show caption, to enable caption if you want to enable caption in other languages. So, today's session will be for 2 hours. Basically, the first part of the session will focus on AI for agriculture, which will be handled by our speaker, who is already here, Professor Anna Kerner. And the second session, AI for forestry, will be handled by Dr. David Dow. Now, I am Oluwafermi Oladipo, an undergraduate student of the Federal University of Technology, Accra, here in Nigeria. I will be handling today's session with Dr. Barbara Temple, who is also right here with me. So before we begin, I would like to introduce our speaker. Our speaker, Professor Anna Kerner, is currently an assistant professor at the Arizona State University, the School of Computing and Augmented Intelligence. Our research focuses on developing machine learning systems for real-world data use and other use cases. She's a machine learning and AI learning lead for NASA Avis and NASA ICAS, as well as Center for the Arizona State University Center for Global Discovery and Conservation Science. She was recently recognized in 2021 as one of the Forbes 30 under 30 list in science. Professor Anna, it's good to have you here today.
Thank you. Thanks everybody for joining today. it's really incredible to see 337 and counting people who are joining us live. I know it's 10 a.m. here in Arizona where I live, but it is probably the middle of the night for many of you. So I'm really grateful that you took the time out of your days and nights to join us here live for this lecture. So today we're going to be talking about AI and agriculture. And if you're wondering, hey, I thought this was the climate change AI summer school, not the agriculture AI summer school. You're wondering, what is the connection between agriculture and climate change? And maybe many of you already know this, but climate change, people are often thinking about, greenhouse gases, carbon, weather, atmosphere, all these different things that are not necessarily what is exactly happening on land. And that's really what today's sessions are diving into. We're talking about agriculture here, but later you'll hear about forestry as well. And you'll find that these ecosystems or these land uses really are both drivers and susceptible to climate change. So agriculture is one of the biggest contributors to climate change, but it's also one of the most at-risk industries to climate change. So some of the effects of climate change on agriculture are that changing temperatures and changes in precipitation patterns, for example, more or less intense rainfall or changes in the timing that rainfall occurs, can significantly reduce crop productivity. We also see increased frequency or intensity of extreme weather events, such as droughts and floods that cause serious crop loss and damage, and reduced water due to the effects of climate change also makes it more challenging to grow crops that are especially water intensive, and increases competition for resources among not just agricultural producers and countries, but among various land uses that require water. So on the other side, where agriculture is also intensifying climate change, we have livestock, rice production, fertilizers, for example, that are emitting greenhouse gases such as methane and making this situation worse. Land use changes are frequently occurring due to agriculture, where forests or grasslands are cleared away in order to make way for agricultural land for growing more crops. And in addition, the health of our soil is being degraded, particularly by large-scale monocropping, resource-intensive systems, which reduces the ability of the soil to sequester carbon and degrades the overall ecosystem health. So agriculture is a really critical component of studying climate change because it is both one of the biggest drivers as well as one of the biggest at-risk industries. And all of this, of course, intensifies a global problem of food insecurity, which many, many people in the world face and remains one of the biggest challenges that we have today. So as climate change intensifies, so does food insecurity. And so this makes the Sustainable Development Goals of zero hunger and climate action very closely tied together. And so many of the techniques or solutions that we might try to develop to address one of those is often affecting or affected by the other. So we need to be able to deliver information to decision makers to help them make more informed decisions about how climate change is influencing agriculture, how agricultural productivity is going, and how agriculture is influencing climate change. So who are these people that we need to deliver information to? We have a poll set up for this that I think the TAs will share some of your responses to as they're coming in. I think you're also welcome to add your answers in the chat. But I want to hear from you all. Who is it that needs this information? TAs, do we have any answers coming in yet?
Yes, around 100 people answered.
Could you just read
Let's
out
wait
some of them for us?
1 minute, yeah.
Okay.
So in the chats book, we have people mentioning farmers, governments, civil society, consumers, humanitarian organizations, Department of Agriculture, all stakeholders along value chains, industries.
Great, thank you. These are all great answers. There's so many people who need this information. I think you guys got all of these. There are farmers who want this information, policymakers, which can also include people like the Department of Agriculture, departments of statistics, all kinds of organizations in governments, as well as aid organizations or NGOs, consumers, economists, agronomists. There's many people who are involved in the very interconnected global food system. So we're going to zoom in on a couple of those here, looking at both farmers and policymakers. So if we zoom in first to farmers, what kinds of questions do you think farmers want answers to? And we can get your ideas in another poll here. Okay, I see a lot of things coming in the chat. So I'm seeing a lot of crop yield. So how is climate change impacting crop yield? Forecasting the onset of rains, knowing better information about the weather, drought, soil moisture, all kinds of things that are related to where to plant, how to conserve water, pest related information. Yes, these are all great answers. So let's keep going. Feel free to keep adding your answers in the poll. But yes, these are all things that farmers would like to know related to climate change and how they're growing their crops. So one example of this, again, is the changes in rainfall, where we see that climate change is changing the intensity and the timing of rains. And in particular, in regions that are predominantly rain-fed agriculture, this is especially challenging for farmers and can lead to significant losses of yield potential and crop production, and of course increases in food insecurity as well, because farmers are generally planting according to seasonal timelines of rains that have been happening very regularly for a long time. But as climate change is disrupting those more and more, those kinds of traditional schedules are not really working anymore for farmers. So information about the timing of rains and other factors can help farmers understand or decide when to plant. They can also get information about how crops will perform or might perform in different conditions. They can learn about potential threats to their crop production. So, for example, how might climate change be likely to affect production where they are growing, as well as actual threats to production like pest or disease outbreaks nearby, or short-term weather forecasts. Many of you mentioned soil moisture, rainfall, temperature, these different factors. We heard about yield, so potential productivity, not just what is my yield going to be, but what could my yield be under ideal conditions? Is there some delta that I could try to increase my yield by? So this example, or this figure here, shows a map of yield gaps in corn or maize, which was produced by a very cool website called Our World in Data. And this is looking at basically the darker red a country is, the larger the gap is between what yield they should be able to attain based on similar climate conditions in other areas and what yield they are actually attaining. So these are areas where yields are really low, and we have a lot of potential to increase yields. And we're going to talk in a little bit about why it's so important for land use and climate change to increase yields. Farmers might also want to know about suitability of crops. So we hear from farmers in many places who want to know, would it be better to grow a different crop given their climate conditions, or as the climate is changing, should they switch to maybe more drought resistant varieties or some other crops? So the second group we're going to talk a lot about are policymakers. So these are people in governments, departments of agriculture, statistics, etc. So if we could launch that poll, I would like to hear from you guys about what you think policymakers want to know. Okay. So benefits, long-term impact of climate change. Might there be ways to increase the resilience of crops? How crop production or increases or decreases in it might affect people's livelihoods, how much water is being used, all these different kinds of things. So policymakers are often trying to understand how climate change is influencing agriculture and how agriculture is influencing climate change, not just right now, but in the future, right? So policymakers are often interested in the short term as well as the long term so that they can plan ahead for these kinds of impacts. So they often want to know very similar things to what the farmers want to know, like crop performance, threats to production, when they should intervene in a situation, how they should intervene, what the potential productivity could be, crop suitability, impacts of policies, etc. But often policymakers want to know these things on a much larger scale. So while farmers are often interested in what is happening on my farm in this one field or in these several fields that I manage, policymakers often want to know what's happening across thousands and thousands or millions and millions of fields in a district or a state or a country or the world. So they often want to know similar things, but on very different scales. So I'm going to talk about a couple of concrete examples of how we're using AI and remote sensing from satellites to deliver information like what we've talked about to the hands of decision makers, especially in policy making instances, but also in some cases with farmers directly as well. So both of these examples come from two NASA programs that I am the artificial intelligence lead for, NASA Harvest and NASA Acres. Both of these organizations try to increase the uptake of satellite data in decisions that are made related to agriculture and food security around the world to help promote increased food security, agricultural productivity, and resilience to environmental and climate changes. So Harvest is working at the global scale, whereas Acres is focused on the United States. So the first example I want to share is from NASA Harvest in a project where we work with an organization called FuseNet, which is part of USAID, which stands for Famine Early Warning Systems Network. And FuseNet has the mission of providing evidence-based analysis to help the government, decision makers, and relief agencies to plan for and respond to humanitarian crises. And those humanitarian crises can be caused by many different things. But in general, what they're doing is their early warning team is running this thing called the household economy analysis, which is a system that forecasts how shocks will affect households. So they can, for example, determine what needs for additional help households might need. And they can deliver some early response, for example, in the form of income assistance or some form of aid. And those shocks can be due to climate or weather related issues. So for example, flooding. This recently occurred in Kenya. I know many of you in the chat are in Kenya. And so you experience widespread flooding very recently. But it could also be from conflict, which is not the subject of this session, but is also very much impacted by climate change. So conflict is also a major driver of food insecurity. And so FuseNet often needs to know the answer to what the impact of some extreme event is on crop cultivation in a given region so that they can incorporate that loss or potential gain in some cases into their household economy analysis. So when there is a shock or extreme event that occurs, FuseNet is able to send our team a request for analysis to provide an answer to this question, where we can say that this event, this extreme event in a given region corresponded to some measurable change in the amount of crop that's being cultivated. So this year, over the past year, we've worked on a use case in Sudan where I'm not sure if anyone in the chat is from Sudan. I didn't see all 430 people, but likely somebody is. But many of you are probably very familiar with the ongoing civil war in Sudan, which has seriously impacted the ability of farmers to cultivate their crops. And so FuseNet sent us this request last year to try to estimate the impact that the war had on cultivation in Sudan. And so we were able to get this request in September, and using these AI techniques and the widespread availability of satellite data to get this answer to them months later, that cultivated area in Sudan had decreased at least 20 to 30% in 2023 compared to the prior year. And so this kind of information can help decision makers or policymakers to provide early response, but also to incorporate these impacts into planning for the future. Another example, this one is from NASA Acres, where we're working on AI and remote sensing for agriculture in the United States. We're working in Maui County in Hawaii, which is a state made up of several islands. And Maui County has 3 islands, Maui, Molokai, and Lanai, that are populated. And food security is a major issue there because the majority of their food currently is being imported, which is extremely vulnerable to disruptions in supply chains, but also very vulnerable. The Hawaiian Islands are one of the most vulnerable places on Earth to the effects of climate change. And so getting more information about agriculture status and productivity and conditions is very important to policymakers as well as to individual farmers who we want to be able to enable to increase their productivity without making things worse for the ecosystem or for climate change. So farmers really want to, and policymakers there really want to increase productivity in a sustainable and regenerative way. So we are working on developing AI systems that can extract these variables from satellite data and provide information in this food security dashboard to end users like Maui United Way, Department of Agriculture, farmers, the county council, et cetera, to help them make more informed decisions about how to increase agricultural production sustainably. So both of these examples were over quite a large area. And so those might have been surprising examples because people usually think of climate change, or people usually think of agriculture and AI as being these like precision agriculture on-farm systems. You've probably seen different pictures of, a drone that's farmers flying a drone maybe, and it's reading things about the soil and they're getting it in an app, and there's like robotic weeders, there's all these kinds of things happening on the farm. And that does happen, but it's extremely rare with respect to how many farmers there are on Earth. So these are very effective technologies that people are studying, and we are going to talk about them today. But we're also going to talk about a perspective that you might not be as familiar with, which is using data from the sky, from satellites that are orbiting our planet. So we've had hundreds of satellites, or currently we have hundreds of satellites that are orbiting our planet and collecting Earth observations. And these satellites have been recording data since 1972. So we have over 50 years of data from satellites. And these satellites are recording observations regularly all over the globe in very, with well-calibrated sensors. And most of it is free, which is really amazing. Most of it is freely available from NASA and the European Space Agency. And so there's a huge amount of information that we can extract from this free archive of petabytes of data that is just waiting for us, not just for agriculture, but for other elements of climate change that you'll hear about in this summer school. So the way this picture works is we get this data from satellites, and from that we have this time series stack of observations from multiple different satellites. And we pair that information with ground truth data that we have from extension agents or agronomists or farmers, can come from a variety of sources, but basically gives us the labels or our calibration data of what we're actually seeing in the satellite observations. And we can give this data to our machine learning or deep learning models to try to predict higher level data products that contain information that is closer to what decision makers need. So where are crops growing and where are certain types of crops growing? That's called cropland and crop type maps. maps of crop conditions. So how are crops doing? Are they doing poorly? Are they doing well? Yield modeling, so trying to estimate what the yield will be of those crops. And we can give that information to those end users or decision makers like policymakers or farmers to start answering some of those questions that you all brought up at the beginning of this lecture. And often we've kind of figured out what these baseline data products that are needed for decision makers to be able to start answering some of those questions. So for people to know, for example, what the effect of increased drought in the future will be on crop productivity, they need to know where the crops are to begin with, which might seem like something everyone should know, but actually getting maps of where cropland is at any given time is still a really hard problem. Then there's also more complicated questions like where are crops actually active, or where are they fallow? Where are the rangelands where livestock is being cultivated? Where are the grasslands? Where are specific crop types, not just cropland in general? All of these different spatial layers that tell us kind of the fundamental building blocks that we need to try to answer those questions. And then that information can be paired with things like data sets of field boundaries, so where the actual individual farms are, not just where they all are in general spatially, but actually start to have objects of individual farms. So I know not just what are the conditions in all of Kenya, but what are the conditions on my farm in Kenya, as an example. And then this information, which have been called essential agricultural variables, or EAVs, this can be combined with other information like soil moisture, evapotranspiration, vegetation conditions, all these different variables that we can get from satellite data to actually give specific information to decision makers. And to get these fundamental products like cropland masks and crop type masks and field boundaries and yield and area from satellite observations, we need machine learning. We could do it manually, but that would be extremely tedious and would cost a ridiculous amount of money and human effort. Imagine looking at the entire world and delineating every single farm boundary. It just is not a feasible solution. So due to the scale of the data here and the frequency that we often want to update these products, we really need AI and machine learning to do this for us. So that is why in the first part of this next piece of the lecture, we're going to talk about a kind of survey of methods in several of these areas. So several of those variables that I just mentioned: cropland maps or crop mapping, crop type mapping, field boundary delineation, yield estimation, and we'll also talk a bit about pest and disease detection, which are really the core topics that are being studied at the intersection of AI and agriculture and remote sensing. And later in the lecture, we're going to survey some other techniques in the intersection in the top left here of kind of on-farm solutions with proximal sensing. So all of these terms or all of these tasks, crop mapping, crop type mapping, et cetera, are agriculture specific, but they all map to pretty well-studied problems in machine learning. So crop mapping is basically binary classification. Crop type mapping is a multi-class classification problem, or sometimes a binary classification problem. Field boundary delineation is basically segmentation or instance segmentation. Yield estimation is a regression problem. And pest and disease detection can be framed in several different ways, but we'll talk about it in terms of out of distribution detection or outlier detection. And within all of these tasks, there are very interesting problems that are raised for not just machine learning applications, but for the broader machine learning community to study in terms of domain adaptation, distribution shift, data fusion, learning from limited labeled data, and many more problems. So these use cases are not only impactful, but they motivate a lot of challenges and specific use cases for studying challenges that are wide-reaching in machine learning. So why are we talking about crop area and crop yield? I want to give a couple of additional examples here to illustrate, again, the link between these variables and climate change. So in particular, what I want to convey is this push and pull between crop area and crop yield. So crop yield is basically the efficiency or a rate of crops that we can extract from a unit area. So yield is measured in kilograms per hectare or tons per acre. Basically, it's an amount per unit area. And crop area is, of course, the area in hectares or acres or whatever unit of measure that we're using for cultivation. And so if you think about crop production being, the key variable that we want to measure, production is the rate that we can yield crops from a unit area, for example, kilograms per hectare, times the area that we're growing that crop over at that yield. So that area in hectares. So if we increase yield, if we imagine keeping our production fixed, if we increase yield, we're able to decrease the area that we need to produce the same amount of food. But if we decrease yield, if we have low yields, we have to increase the amount of area that we use for cultivating crops. And so this is where, optimizing yields can be a huge boost for land conservation by sparing land that's needed for agriculture, because we're able to grow crops more efficiently on less area. But of course, the flip side is true as well, where if we can't grow crops as efficiently, we need to expand the land that we're using for agriculture in order to meet our food needs. So this plot here, again, from our World in Data, is showing the amount of land that has been spared by increasing yields over the years. So there's been a lot of research into increasing crop yields since 1961, when this timeline starts. And so you can see that the land globally that is being used for producing cereals has not increased that much compared to the amount of land that would have been needed had we not increased crop yields over that time. So this basically shows how beneficial policies that increase yield can be as a strategy for conserving land that would otherwise be needed for agriculture production. And in another example here, this is just a study of two places. So in South Asia, let me say first, globally, food production has been increasing, of course, to meet a growing population, and will continue to need to increase everywhere. But how that production is increased varies globally. So is production increasing because of increasing yields, or increasing because of increasing area? And in the case of South Asia, they were able to increase all of their food production through higher yields. So basically, land use has not changed very much since 1980, but the amount of food produced has increased significantly. And that's driven by increasing yields. Whereas in sub-Saharan Africa, again, if you remember that map from earlier, where we saw those big yield gaps, largely because sub-Saharan Africa is one of the most at-risk, vulnerable regions to climate change. And those yields have really not been increasing very much, whereas land use has more than doubled in order to increase food production. So that is a big target for increasing yields, not just for food security, but for land conservation for many countries in Africa.
Sorry,
So
you have 20 minutes to go.
no, okay. Let's speed up then here. Thank you, Barbara. So crop mapping is this task of binary classification of pixels in satellite images as either crop or non-crop. So the output is basically a binary mask like this on the right. And so I'm going to survey pretty briefly, but you can go back and find these papers if you're interested in reading more, several different methods for these tasks that we're talking about. So crop mapping, as an example from a project we did here in this paper in 2020 in Togo, we trained a recurrent neural network called an LSTM, a long short-term memory network, on time series inputs from satellite data to predict whether a given pixel contained cropland or not based on the temporal signature of that location in the satellite observations. And using this technique, we were able to predict a countrywide map of cropland in Togo at 10 meter per pixel resolution, which was enough to capture much of the smallholder agriculture area in the country and deliver that to the government for use in their farmer support programs during COVID-19. Crop type mapping is similar in terms of getting this kind of discrete output from satellite data. But in this case, we're interested in specific crops, not just cropland in general. So we want to know, where is maize specifically, where is soybean specifically, or other crops. And so this could either be a multi-class classification with n classes as the output, or it could be a binary classification where we say maize versus not maize, for example. And here is an example from a recent paper called VITS for SITS, Vision Transformers for Satellite Image Time Series, which was published in CVPR, that basically designed a specialized temporal encoder for satellite data to be able to more accurately predict where crops are growing, specific types of crops are growing. And again, this could also be pitched as a binary classification problem of one crop versus the rest, or one crop versus everything else. And this is an example where we've done this in Maui County with the project I mentioned earlier, as well as some other use cases using a time series transformer with several satellite data inputs, which I'll dive into a little bit more towards the end. Field boundary delineation is the task where we want to segment individual field boundaries. So we have some satellite data and we want to pick out the polygons of each individual field that we can see. So on the right, you see the example ground truth of what the field polygons that we want to pick out are. So here's an example from a paper by Sherry Wong and team, where they used satellite data from PlanetScope, which is at 3 meter per pixel resolution, as well as high resolution data from Airbus and used transfer learning in order to train models on plentiful labeled data of field boundaries that were available in France, and transfer that model to a data sparse or label sparse setting in India, where they had much fewer labels. So by pre-training the model on data from France and then fine-tuning that model on weekly labeled images from India, they were able to produce a model that could predict field boundaries in India as well as France. Yield estimation, again, I mentioned, is a very important problem where we want to estimate the amount of crop that is going to be harvested or has been harvested per unit area. For example, kilograms per hectares. So in this example, Jillian Daines et al. In 2020 predicted the maize yields for the United States all over the country over multiple years in order to identify areas that were high producing or low producing. There's also many other techniques that have been published in the literature for estimating yield. Again, this is a regression problem, so we're trying to predict this continuous valued yield estimate. And this is an example you can read about more if you're interested, from our group that developed a method called task-informed meta-learning, or TIML, where we evaluated the model on this task of yield prediction in different counties in the United States based on satellite time series, where the model is able to consider not just the time series, but the specific task definition, particularly which county is being predicted in order to more accurately predict soybean yields at the county scale. In predicting pests and disease, or just generally hotspots within fields that farmers may need to treat early, the goal is to detect anomalies within fields that represent some unfavorable growing conditions. So to give you an example of this, on the left, we have an image of a field that has some disease outbreak in the middle of it, where it's pointing to with the red arrows. And on the right, we show the anomaly score from a method that we have called DORA, which is Domain Agnostic Outlier Ranking Algorithms, to score the anomalousness of each pixel within a field boundary. And this is just how DORA works. Okay, so that was a survey of methods at the intersection of AI and agriculture and remote sensing. So these very large area studies that are often useful to decision makers and sometimes farmers directly. But now we're going to take a look at some methods that are kind of more at the field scale, using on-farm equipment, precision agriculture types of solutions. So precision agriculture, again, is this data-driven management of on-farm resources. So for example, scheduling when watering should happen or when different nutrients should be applied. And this is probably what a lot of people might be familiar with. So in this example from Wu et al., for optimizing nitrogen management, this was done using deep reinforcement learning algorithms and crop simulations with this tool called DSAT GYM. So basically a simulated reinforcement learning GYM for running these crop simulations and what the impact of different policies from a reinforcement learning agent might be. So they wanted to learn a policy for nitrogen application that minimizes the input, or how much nitrogen needs to be applied, and the leaching of that nitrogen without jeopardizing the yield. And so they trained their policies using a deep Q network and this GYM DSAT interface in order to simulate those interactions of the environment and the reinforcement learning agents. And using this reinforcement learning policy, they could achieve higher or similar yields to without using the policy, but were able to achieve lower fertilizer use and lower leaching for their experiments. Another example is in robotic farming. So people often want to automate the tasks that robots or other equipment need to perform on farm, such as weeding, spraying of herbicides, detecting pests, all kinds of things like that. So in this example, the authors were able to automatically detect what was weeds and what was actually crop, and spray only the weeds and pass over the crops using this small robot. There's also yield estimation methods for actually on farm. So if you're all the way on the ground, you can actually estimate the yield directly from what can be seen. For example, with fruit trees in this work, they're able to count the yield from fruit trees using drones combined with deep learning segmentation models. And pest and disease detection, this also is happening at the field scale. So if people can actually go into the farm and take pictures of the disease, there are apps and different methods for identifying what kind of disease or pest is there and providing recommendations about how to treat that. And finally, there's lots of methods also within livestock and rangeland management where people try to monitor and optimize animal behavior, their health conditions, and their feeding patterns. So in this example, they're trying to automatically score the conditions of dairy cows and react accordingly. There's also lots of work in kind of automated forage management, different ways of better managing livestock with AI. So we're going to do a quick deep dive into one of these methods, one of our recent methods from my own team, to kind of give you an idea of how one of these specific methods might work. So in this technique that I mentioned earlier is a method that we use for crop type mapping. I'm going to talk a little bit about how we do that. So this method is an instance of a self-supervised model, which many people might call a foundation model for remote sensing. And so I'm guessing almost all of you, if not all of you, have heard about foundation models and self-supervised models at this point in the era of ChatGPT. But we can also build these self-supervised models for remote sensing data in order to pre-train a model leveraging this huge archive of remote sensing data that's unlabeled. Like I mentioned, we've been collecting since 1972, and train a model that can be used for more efficiently fine-tuning or adapting to a variety of other tasks, not just in agriculture, but in a variety of applications where you might need satellite data. But in this instance, we're going to talk about how it's used for, well, we'll talk about how it's used in general, but in the example of crop type mapping. So the model that we've developed for this is called Presto. And Presto, the design of it was inspired particularly by agricultural use cases because of our ties to these specific needs in agriculture and food security through NASA Harvest and NASA Acres. So it's particularly inspired by agriculture, but we've also designed it particularly to be adapted to the specific character of satellite data and what we can measure in that satellite data. So Presto stands for the Pre-trained Remote Sensing Transformer, and this is the name of the paper if you want to read more about it. But Presto uses lots of different input sensors at pre-training time. So it uses not just one satellite sensor, but it uses multiple, as well as these different higher order products like land cover maps from Dynamic World or elevation, for example, to pre-train the model to understand patterns of what can be seen in remote sensing data. And the training task that we use, or the pretext task for pre-training, is a masking strategy. So this is a masked autoencoder where we apply structured masking, where we basically delete entire channels or entire instruments, entire chunks of time steps from what the model can see in order for it to try to reconstruct what was there in the beginning. And it does that using a masked autoencoder transformer. So a quick refresher about transformers. Transformers are a type of neural network architecture that was originally designed for sequence modeling, for language in particular, where we have these stacked blocks of transformer blocks, which consist of self-attention and feed-forward neural networks, essentially. And so there are many of those blocks stacked in an encoder as well as a decoder. And the model is taking in a sequence of tokens, such as these language tokens here, and produces some output, for example, another sequence. So in this example for machine translation, if the input is je suis étudiant, then the output might be the translation, I am a student. And so if this is a masked autoencoder, the model is not just trained to do this translation, but it's trained to do that if part of the input is masked out. So our input then is je blank étudiant, and the model has to predict what comes in the middle there, which in this case would be je suis étudiant, or can be the translation. So in the case of satellite data, maybe we have a time series of some vegetation index like NDVI or some other sensor, and the model is trained to fill in what the missing data is during pre-training in order to predict what was masked out in the input. And so this is pretty much exactly what Presto does when we pre-train the model, using all of these input sensors that you previously saw, Sentinel-1, S1 here as an example, and encodes those different sensors and passes them through an encoder and decoder in order to reconstruct them at the end. So that's basically this masked autoencoder component of Presto, and using its transformer model. And we use a time series. All of these inputs are time series, not actually images. So this is a time series transformer, not a vision transformer, which gives us much smaller inputs than if we had large images, for example. So using Presto, once we've pre-trained it in this way, we have a model. We just take this encoder part of the model, and we can mask out the missing time steps or channels if we need to, depending on our task. And we can pair this now with our fine-tuning data set or our small data set of labels from on the ground, for example, where taro is being grown in Maui. And we, for each of these locations, can extract the Presto features or the embeddings from that encoder output and train a smaller classifier like an MLP or a random forest to make the predictions of taro or not taro, or taro or some other crop using that ground truth data. And we find that Presto does...
Prof,
oh,
you have a few minutes left.
Yes, we're almost done here. Okay, so basically Presto performs much more efficiently than a lot of compared models, and does so very efficiently. So this is very accessible. You can do this on your own with this small code block here, and be able to fine tune on your own computer in minutes. So I'm just going to really briefly cover some of these challenges in doing this. So it seems really exciting, and it definitely is, but of course, like many things, actually trying to do this can be really challenging in practice. So some of these challenges that we face are difficulties in getting ground truth data, which is very expensive and difficult to acquire. Often our benchmark data sets are not really reflective of the real world conditions that we see on the ground, for example, with intercropping. there's a really huge difficulty of generalizing our models across places in the world and across time. And this is getting better, but there's still quite a lack of open data and code for being able to build on research in this area. And of course, doing all this communication with end users and deploying models and actually trying to realize those benefits on climate change and food security is a huge amount of effort in terms of time and funding. So I will leave us here. I can try to answer questions in the chat if we have time. I think we might need to go to the next session. We'll let the TAs tell us. But if you're ready to get started, here are a few resources from our team that you can check out, or you can reach out to us and we'll try to answer your questions as well. Thank you.
Yeah, thank you very much, Prof. Anna, for this wonderful and enlightening session. Honestly, I myself have been able to learn a lot. Due to time, we will not be able to answer the questions now. We'll be answering the questions in the community session, in our community platform. Speaker will be providing answers to these questions and we'll be posting them on our community platform after today's session. So right now, we'll be moving on to the second part of our session for today, which will be handled by Dr. David Dow. The session is on AI for forestry. Dr. David Dow is right here with us. Dr. David Dow is a founder of the nonprofit Gain Forest and a semi-finalist of the X Prize Rainforest, where he co-leads the ETH Zurich plus Gain Forest team. He's a PhD degree holder.
It seems we lost Oladepo, so I will take over. So welcome again, David, from ETH. And he's going to talk about AR for forestry. David Dow is the founder of the nonprofit Gain Forest and the semi-finalist of the X Prize Rainforest, where he co-leads the ETH and the Gain Forest team. He received his PhD here in Zurich and was previously an engineer in Silicon Valley and a research fellow at the Berkeley AI Research, Stanford, and the Broad Institute of MIT and Harvard. So welcome again. And we are looking forward to listen to your presentation.
Thank you so much. So I'll start sharing my screen. I'm super excited to be back to give the Forest and Land Use lecture here at CCAI Summer School. So I need to make sure that I share the sound. Second, but why am I not sharing the sound here? Let me try again. I don't think I can click on sharing the sound here.
We don't see your screen yet.
Select this option if you want others to hear the sound coming from your computer, but I unfortunately cannot share it. Let me try it maybe like this.
No,
like this. And then you just need to tell me if you can hear it. And if not, then I will try to reshare it again. So sorry for that. So, but I don't seem like I could click on sharing the sounds, because sounds is going to be really important for this lecture. Sounds is one of the ways we connect with nature, and therefore I want you guys to hear it. So let's see if it works. And if not, please write in the chat. So welcome to the Forest and Land Use or Land Systems lecture at CCAI Summer School 2024. I'm David. I'm the co-founder of Gain Forest Earth, which is a nonprofit based in Zurich, that tackles the biodiversity and climate change crisis using technology to protect forests around the world. I'm also the co-lead of ETH BioDevX, which is, I can proudly announce we're not semi-finalists anymore, we're finalists of the X Prize. That will be happening next month, actually, in Brazil, where we're competing on monitoring forests efficiently with new technologies. So I am super excited to give this lecture. My PhD has been in AI, but as you can see from these pictures that I love to share, you don't see a lot of computers here, but there is actually a lot of like artificial intelligence happening in the background. But this is basically, ever since my PhD first week, I came up with an idea of a nonprofit that uses initially remote sensing to monitor forests. And when you don't cut down the forest, it automatically triggers a payment to the communities that protect it, right? This idea was founded in a hackathon. I called it Gain Forest. It won the first prize of this hackathon. And I really fell in love with this idea and decided to make it a proper nonprofit afterwards, and dedicated many years of my life to build it up, realizing remote sensing is definitely not sufficient to protect nature on the ground, because you need to go on the ground. And I happen to had the pleasure to visit many communities around the world to build up this nonprofit. And this nonprofit now, gainforest.earth, is based in around the world, and it has 28 partner organizations where we work with. We work in Kenya, where we help monitor wild elephants, for example, crossing the road here. We work, for example, in the Philippines. We are strongly represented where we are empowering communities to measure trees and mangroves on the ground. And of course, in Brazil, where we are teaching drone monitoring and decentralized monitoring, reporting, and verification for the local communities. More on this later. So this lecture it's a little bit my hope to show you why this topic is so fascinating, forests and land systems. And we will start with first, what does this have to do with climate change, like forests and lands? So like a really quick primer on the connection between the forest and the land and our climate. Second, okay, now we understood what it is and how it's important on climate change. What are people doing and governments doing to save forests? So we'll talk a little bit about nature finance, we'll talk a little bit about nature regulations. There has been a lot going on this year, so there's a lot to share. And then, of course, this wouldn't be a CCAI lecture without the AI part. We're talking about artificial intelligence and how it can help tackle some of these big problems that forest faces. And we talk a little bit about a special part of it called equitable AI, where we're specifically focusing on the roles of indigenous people and local communities that are collecting frontier data. And hopefully you have some time to talk later about future work and a little bit of discussions as well, what's coming up. So climate change, forest and land systems. And now the part where I'm not sure if it works, but tell me if you can hear it. No, right?
We hear.
Nice. So this, I always like to start my lecture like this because it kind of grounds us back to why we're doing the things we do. You can close your eyes, you can listen to the sounds of the forest, the birds singing, and you can just imagine what nature is. And many of you might, so I'm based in Switzerland right now, think of water and mountains. Of course, you think of forests, some think of ocean, right? But definitely it's very clear the life, the biodiversity that it connects, and how good we feel about this when we hear these sounds of nature. And so this is not unusual. This is actually quite important because we humans co-evolved with nature. We come from the trees down. So nature is really essential for us and for our human existence and our good quality of life. Most of nature's contributions to people are not fully replaceable. Some are even irreplaceable. So this is not me. This is the Intergovernmental Science and Policy Platform on Biodiversity and Ecosystem Services, the world's highest expertise when it comes on nature questions for policy. And that is a strict reminder that when we talk about forests, oftentimes we hear forest carbon credits, how forest stores carbon. That's not everything that forests provide us, right? Like forests actually have four different kind of really important, or nature itself have four different kind of really important things that they provide. It's a regulating factor where storing carbon is just a little bit of it, purifying water, control flooding, cooling the temperatures. But then on the other hand, you have supportive functions like photosynthesis, biodiversity, which we just heard, food, and then you have provisioning features such as clean water, fish, wood, pollination, and the thing we just felt when we listen to these sounds, right? The calmness, the tranquility, it's aesthetics, recreation, and just stewardship. This is something that is really important that nature gives us. And this big circle is something we call ecosystem services. These are the services that nature provides us for free. But when we look at carbon, and that's where the connection comes into climate change, right? Like climate change is triggered through global warming, which is triggered through the emission of greenhouse gases. Much of the carbon that is stored is either in the trunk of the tree, so we call it above biomass, which is the green circle, or, so you can see tropical forest has some of the largest above biomass because they are huge trees, or they are stored underneath in the ground. For example, if you look at the wetlands, a lot of the carbon is stored in the soil. Carbon is the essential molecule of life. So if you have a lot of bacteria, if you have a lot of life, a lot of biomass is actually stored underground. And that's where the carbon storage comes in. And that's also where the problem comes in, because we humans have not treated Mother Nature very nicely. In fact, the natural world is deteriorating in rates unparalleled in human history. We have lost half of the world's forests that ever existed so far, and it's been increasing. These are satellite images, for example, of Mato Grosso in Brazil, where we have strong deforestation rates happening, and that results in all that carbon storage being unleashed. So if you look at, for example, just the statistics of how humanity has treated forests, a third of the forest has been destroyed by expanding agricultural land, much to grazing lands, pastures for cattle, crops, a little bit for urban planning. And then the worst is also that much of this deforestation, so this is anything that's below, which is negative, is forest loss. And anything that is like brown forests and areas in the global south are tropical forests. You can see this large dent, especially after 1920 to the 80s, where large deforestations are happening in the global south, while actually starting from the 1990s, Europe and the global north has a rebound in forest. We used to cut a lot of the forest over the many centuries before, but ever since, this is quite an economic natural phenomena. Once you have a decent amount of wealth, people care more about forests or have more spending on nature, and then you can see this bump of restoration that is happening currently in Europe, and you will also see it in a second with the laws that are coming in Europe as well. But really, the problem here is you just saw how this carbon is stored underground or in the biomass above. So as forests are, you must have heard, the lungs of the earth, storing a lot of the carbon coming into. They are not, when you're not treating it well, when you're actually burning down the forest, much of the carbon that is stored in the tree, instead of a carbon storage, becomes some kind of a carbon bomb, where all the carbon that has been stored beforehand in the tree gets released back into the atmosphere. And it's actually a key driver of the climate crisis. I was surprised the first time I heard these numbers. Deforestation is responsible, estimates between 14 to 18% of global anthropogenic emissions. To just give you an idea what that means, if tropical deforestation would be a country, it would be the third largest emitter in the world, right after the US and China. So there's literally no way we can anything that the Paris Agreement, the 1.5 degrees, hopefully below 2 degree global warming, we cannot achieve that if we cannot stop deforestation in the next couple of decades, very soon, hopefully. And it's not just clear cutting the forest. In fact, of course, when you burn down and clear cut the whole deforested area, you can see it on the right side, all the biomass burning and the decomposition goes back in the atmosphere, the carbon. When you have an intact forest, there's actually a balance between photosynthesis and above ground respiration. So when the forest has grown in full size, there's not a lot of extra carbon that the forest will store. But if the forest is getting degraded, for example, through droughts, stress, fire, logging, edge effects, then already the biomass loss and therefore the emissions will be stronger and bigger than the photosynthesis and regrowth, and therefore it becomes a net emitter of emissions. So degradation is actually a huge part of the emissions that are coming in, not just the tropical deforestation, the clear cut. And so there's a quick quiz for you guys. So what are the drivers of forest loss? We have seen already from the side imagery that you can recognize forest loss. Here are 5 different kind of side pictures of 5 different drivers of forest loss. And I think there will be a quiz coming up now where you can type in A, B, C, D, and E, what these different drivers are. So I'll leave you a minute for this. No, I think I can see the results then. Here, yeah. Wow, we have so many people listening from around the world. Like I've never seen so many like answers coming in from my from my Zoom poll. So super exciting to see that distribution like shaping up 230 replies already. But just a quick question, you could hear the sounds before that, right? That was okay.
It was a bit silent, but we could hear if we really wanted.
Okay, so I think it's not because I'm sharing the sounds, but because it goes through my microphone. But then I will just max out the
yes, please.
Work. Cool. I think we have 62% participation now. Interesting. Yeah. So I'm giving it like maybe a couple more seconds. So if you haven't decided which is the drivers of forest loss, then let me know. I think we're good. So I'll share the results. Most of you have said B is the major driver of forest loss. And then A is next, and then E is the first one. So some of you might recognize what B is, but I will reveal the results now here. So let me just hide this. You can see that actually B is the least driver of forest loss. It's just 1% of all the forest loss is from B, which is urbanization. The largest ones, the ones who guessed it, 2 is correct. This is deforestation. This is clear cutting. This is, for example, a cattle farm, a pasture that you can see. Then you have forest products, which is basically timber plantations that are recycled overall. This is responsible for 26% of global forest loss. And then you have very strong ones like shifting agriculture. This is like logging, like precision logging, community-based logging. And then you have the wildfires, which is what you can see, this brown scarred, this burned forest. And wildfires have been actually increasing over the last years. And this makes 23% of forest loss. So when you look at the climate crisis, this is a very famous, of course, graph of the increasing temperature, blue to red over 1970 to 2018. But one of the things that people oftentimes forget when it comes to forest, it's also linked to a biodiversity loss. We oftentimes, when we tackle or talk about land systems, land use change, we often talk about this twin crisis we're having. First, the increased temperature that is coming through climate change, that also results in a huge biodiversity loss and vice versa. So this is something that oftentimes gets ignored due to that bigger crisis, the climate change crisis, but I want to emphasize that the biodiversity loss is extremely important and also something that is united by the destruction of nature and forest, those two crises. And deforestation is changing our climate, is harming people and the natural world. So we must and can reverse this trend. This is citing Jane Goodall, one of my heroes. So of course there's hope to it, and of course we have ways to tackle things. One of the ways, for example, is the 1 trillion tree initiative. So there's still 1 trillion trees of reforestation potential. There are arguments on how much potential emissions cuts that will provide to the world when we are able to actually reforest everywhere we can plant a tree. People say up to 10% of emission cuts can be performed by this, but there are ongoing restoration initiatives around the world because of the science, for example, from the Crowther Lab. So, which brings us straight to, okay, what our governments are right now doing? What now we understand the problem, the connection between nature deterioration and the biodiversity and the climate change crisis. What are tools, what are things that we currently are tackling this crisis with? So we have forest carbon credits, right? Many of you must have heard about this. When you reforest, so when you plant a young tree, there's an estimated impact of 15 tons of CO2 per hectare per year that these trees that you planted will sequester from the atmosphere. And when you, of course, stop deforestation, you can also claim credits for stopping deforestation. And the estimated impact, of course, if you burn down a hectare of forest, which is much larger than a young forest that you just planted, could be up to 400 tons of CO2 per hectare, right? This is like how much the average Amazon rainforest is storing in 1 hectare of forest. And in between is something we call improved forest management, where you're trying to preserve middle-aged trees. You're trying to plant new trees. You're trying to be economically and cut down older trees. And this is something that is in between reforestation and avoided deforestation. It also rewards you currently with carbon credits. But there's also many, many other ways how governments are currently financing nature. There's payments for ecosystem services. This is the concept when landowners are compensated for protecting the forest. So this is how gain forest started initially with, okay, you don't cut down the trees now, then you get paid. But there are the challenges, okay, who owns the land? What are the right KPIs? Who monitors that? And then there's agroforestry, which is a land use management system, which trees and scrubs actually grown among crops and pasture land, right? So you have both like intertwined with each other. But here the challenge is market access, and you need kind of an extensive domain expertise to have like your agricultural land managed like this. Ecotourism is a big one, how we pump in finance into nature. Ecotourism is a form of tourism that focuses on conservation of nature and the well-being of local people. But the problem is now, okay, you kind of want tourism, but you don't want it overused because you want to have like equitable benefits and shares to the communities. So you're balancing basically your capitalistic nature to the benefit of the people and nature. It's quite challenging. In this nature regulation side, a lot has happened last year. We have the EU deforestation law when you're based in the European Union. There's now a law that curbs EU contributions to global deforestation. Basically, it mandates that companies that are based in the EU have to ensure that their products do not contribute to deforestation, and that covers soy, palm oil, wood, cocoa, coffee, and beef. There's huge protests, for example, in Indonesia, where now a lot of the products are blocked because it's very, very challenging to verify deforestation-free status, because you need to monitor, you need to understand the land use, you need to understand where your product comes in. This is a huge challenge. And you will actually see the challenge here will be very common in a second. There's, for example, a second regulation that was announced a couple of years ago. It's called the Global Biodiversity Goals, the Kunming Montreal Agreement. that sets ambitious targets, for example, protecting 30% of planet's land and seas by 2030. And this requires also to establish effective mechanisms for monitoring progress and ensuring that these countries are keeping their promise, right, and accountability. And then just last week, the EU Nature Restoration Act came through that is aiming to restore degraded ecosystems across all of the European Union with legally binding targets up to 20%, at least 20% of the EU's land and seas by 2030. And again, the challenge is ensuring compliance, restoration targets, and preventing further degradation. Who monitors that? So you must have heard already the theme of all of this. Nature needs to be protected, but who monitors that? Who is making sure that we are accountable? Because monitoring, reporting, and verification, or MRV in short, is a keystone of implementing all of these policies. It's a key element of protecting nature, and it's a key element for nature finance and regulation. But the problem is we cannot value what we cannot measure, right? And results-based payments, for example, there is $25 billion of promised funds for results-based payments, PES, but so far, much of the funds have not been released because of overlapping land claims, slow performance of measurements, missing trust. That makes all these funds inaccessible to local communities because they have to prove somehow they are protecting it. While on the other hand, they're not sure if they get the money because they're not sure if their proof is enough. And so why would they protect it if you don't know if your salary comes in next week, right? It's very understandable, or like in 2 years or like 3 years. You don't know when it comes. You don't know when the monitoring is enough. And that is because monitoring these areas is just really, really hard. And there's also the problem with greenwashing, right? If you monitor it incorrectly, there has been scandals on these forest carbon credits on that 90% of the rainforest carbon offsets are like worthless. The reports have been going on. And this is, for example, another quiz for you to emphasize this problem. So if you look at this kind of like screenshot from a Brazilian frontier region where the deforestation is encroaching on the left and on the right top, which of these areas do you think, A, B, or C, are the most likeliest to get deforested? So you feel this is kind of a trick question, but take a shot, and let's see what comes out. So that's already good to see that not everyone votes for C, which is the obvious choice. It's actually, oh, interesting. B and C are kind of like close by right now. Okay, I'll give it like 10, 15 more seconds. A lot of you have already voted. Wow. Okay, I think we can share the results. 66% of you have voted already. So this is the first time ever that B and C are exactly the same, 111 votes on each of them. Usually it's C, but I think because I mentioned it's a trick question, you might have like reconsider, but like the answer is, so the answer is most likely C, but we don't know. So I understand why B would be in. For example, you don't know if C is maybe already a protected area, right? That's why there's this really, really strict jump. And there might be even 0% of deforestation risk. So protecting it wouldn't make any sense because it might obviously be a protected area. B would be the most likeliest then, because B has a river access, which is very, very common. You need access to a transportation route, either a street or a river, to start a large-scale deforestation or a settlement. So B would be the most likely. A is most likely the least deforestation risk one. You can see how the problem is already that just from a side picture alone, we cannot really tell because we don't know the land use, we don't know the rules, we don't know if this area has been already a national park and protected. So there is no There is no potential risk. So just from the satellite picture alone, it's really, really hard to see. And that's where the problem also comes in with the carbon credits. This is something we call additionality estimation, or potentially also leakage. If this area is protected, maybe that means that people are just cutting down areas around it, right? Not only that, there's also a second problem that is really big. So listen to this sound clip. It's also a forest, and it's next to the first forest we just listened to. Notice how you cannot hear any dirt. Maybe you can hear this like blip, like this kind of drop, like, and then you can hear a little bit of the rain, but you don't hear any sounds of biodiversity. You don't hear any of these sounds that make us feel very tranquil. And that is because it's also forest, but it is this kind of forest, very close to the first forest you heard. This is a monoculture, a eucalyptus plantation that is only planted for the purpose of carbon credits or timber, because eucalyptus is the fastest growing tree in the world. It grows in full size after 10 years. And then it's perfect for cutting down for timber, or it's perfect for claiming some credits, but it comes with the cost, what we call co-benefits of no biodiversity, and which is really bad, because again, we have two crises that we want to tackle here. So important note here, carbon credits without safeguards can harm climate and environment. So it's really important to have the monitoring ready, to have the measurements ready, to know what we measure in order to value it, right? And now we're coming to artificial intelligence and how it can help. And so you have heard about already MRV as one of the major issues when it comes to nature conservation. Luckily, we're living in an age where we have an explosion of multimodal environmental data. We have tons of field-based monitoring. We have tons of satellite-based monitoring, as Hannah already mentioned in her talk. We have drone-based monitoring, we have environmental DNA monitoring, and we have all other kinds of things. So I argue in this talk here, of course, I'll try to show it to you that fusing and learning from these multimodal environmental data provide us with a novel opportunity and, of course, challenges as well. And artificial intelligence is uniquely positioned to learn a shared representation among all of these data sets in order to improve monitoring, in order to measure the things that we want to value. So machine learning can help us understand the location, health, and ecological value of nature and biodiversity at scale, and ensure that these metrics that are then reflected in policy, finance, and decision-making. So let's take a short look at how AI can be implemented in this whole pipeline that I just explained on payments for ecosystem services, where there's a landowner that stewards a forest site, and he has to provide a monitoring and reporting and verification report to the stakeholders that then pay him for this, right? So currently how it's done, it's quite expensive. There's a third-party certifier that this landowner has to hire, and this third-party certifier manually reports that field data and sends it out. But nowadays, machine learning can be, for example, used to leverage satellite providers and remote sensing to additionally adjust for the third-party certifier. So we can, for example, use remote sensing for deforestation forecasting, land cover classification, driver classification of deforestation, something we just discussed, species identification, carbon estimation. But we can also improve the third-party certifier by replacing that manual and trying to use as much machine learning and AI as possible to connect with the field data. So, for example, a mobile app to connect with field and satellite data, or measuring biodiversity using new sensors like bioacoustic sensors. And then one exciting approach would be to maybe can AI provide us with tools that empower everyone to submit forest data for verification and not just third-party certifiers, so like citizen science approach here. So let's talk about every one of them quickly and showcases how AI can be tackled in all of these instances. So the first question I want to ask is, can we leverage remote sensing for MRV? And if you look at the multimodal imagery sources that we have, Hannah has already mentioned that, but there's a lot of like public data available, Sentinel-2, Landsat-8, 10 meters pixel resolution, and you can see that's something in the left. On the right side, you have commercial data, commercial satellites, Planet Labs and Maxar here. Maxar is Google Maps, for example, the base layer. So this is much higher resolution, 50 centimeters per pixel up to. And you can see the difference when you look, for example, at the site in Brazil one by one. So the challenge for training an AI algorithm here is that these different sensors and reference systems need to be aligned. And also there might be also different temporal information. Maybe this was taken roughly like 10 days ago, maybe at noon, while this one is taking not the same day, but a couple months later, roughly at 4 p.m., right? So you need to kind of align these adjustments in. But if you're able to do so, you have decent success. So this is a example of mangrove classification. On the right, you only use satellite data, and on the right top, and on the bottom, you use satellite data combined with drone data, so a much higher resolution, and you can learn how to align these different kind of data resolution, and it will improve the accuracy of what is a mangrove and what is not. The problem here is, of course, to have the labeled data. So especially in remote sensing and also drones, someone needs to label past mangroves or not mangroves yet in order to have the classifier work. For deforestation driver classification, this is where this other really important data set comes in, which is not the satellite image, but local data on land use, for example, like how is it governed, where are the boundaries of this land, who owns it. So it turns out when you combine Landsat 8 satellite image, this is ForestNet from a past paper in NeurIPS, but I think it's just a very nice, elegant solution where you showcase, okay, if you combine local information in context of where the boundaries end with per pixel classification, you can actually have additional information on what is the driver of this forest loss, right? And this is something that especially these local information on land use or land boundaries are really important to provide you an insight with. Again, the problem again is labeled data. We can also utilize large time series, right? You saw these beautiful or shockingly beautiful like deforestation patterns. In fact, actually in Brazil, when you have deforestation, it looks oftentimes like a fish skeleton, where there's first a very long road, and then there are side roads, and so it looks kind of like a fishbone structure. And these patterns are, if you look and see them happening in much frequency, these are predictable, even though you have unlabeled data. So if you train an algorithm on these kind of predictable patterns that will evolve over time, that's also a way to utilize these large time series. But the problem here is it's huge amounts of data. It's irregular temporal time steps. And so it really depends on the revisit frame rate of the satellites, and also if you are able to get cloud-free images or not. So this is, for example, a very simple example of training a diffusion model to just predict based on Landsat time series, what will it look like you're looking at the first n frames, what are the next like n plus k frames are looking for. And then you can see on the top right is the true forest loss, and the bottom right is the video prediction with UNet that kind of captures the trends, but not so much. Challenges here, again, difficult to train, and you need a lot of computational resources. It's actually something, again, that was mentioned in the past presentation, that is something that a lot of people are now investigating because you have so much of that data. Are there ways to leverage these new advancements of large language models, these foundation models, and see if we can self-supervise these patterns and train it and fine-tune it on downstream tasks such as forest carbon quantification, land cover change, and so on. So this is a part where I think ML is very heavily already used in the remote sensing approach for forests. But then you have also ML being used in field-based measurements. And this is something that I want to quickly discuss next. So for example, there are apps that allow you to take a picture of a tree. So in the past, in order to measure the carbon of a tree, you need to sample it by hugging it, basically. You measure the diameter of the tree, and then you determine the species of the tree, and you put those two numbers into what we call an allometric equation. It can be quite tedious. There are many apps now that leverage on-device compute, edge machine learning models to predict the kind of width of a tree based on the picture. The challenge is, of course, it needs to be low cost, it needs to be on-fly models, and collecting data is still very tedious. Then there are drone-based approaches where you fly above, for example, a tree canopy, and you try to predict the biomass of a tree or the forest itself. Here you can see some predictions of a tree segmentation algorithm. The problem is, of course, limited label data. Someone needs to label the trees. And sometimes, so this is a paper that is currently in submission, sometimes it's super difficult, even for a human eye, to see where does the tree start and where does the individual tree instance ends, right? So this is, for example, the challenge of, okay, instance segmentation versus canopy segmentation. You have the ground truth tree data from 2 locations, Zurich and Tonga, with the blue dots. And then also Zurich has additionally a ground truth like tree height data set, which is really nice. In the middle, we have an algorithm that just predicts where tree canopy is. And on the right, this algorithm is trying to also predict the instance of a tree, like a single tree. And you can see that in Tonga, where the trees are standing in a plantation-like pattern, it's much easier than, for example, for this one canopy row next to the train line here, where it's very, very hard to say where the tree crown starts and where the tree crown ends. And you can see this with the label of the data as well. Then we have recent advancements of drone-based biodiversity measurements, where we can use, for example, reinforcement learning to fly a drone very close and have them attach sensors instead of you going into the forest and attach sensors. This is, for example, attaching a small clip with origami that is work from a collaborator of mine, Stefano Minchev, on the environmental robotics side. And these are ways, for example, how machine learning can be used to replace that tedious sensor attachments into the forest. Going into the forest is quite tedious, quite difficult, and oftentimes very dangerous. So, of course, it would be really nice if machines can autonomously do this. This is something that we deploy during the XPRIZE. We sample environmental DNA, which is a very promising way to capture a signal of life and biodiversity. So you can imagine this to be a really huge COVID test, where the drone flies above the tree canopy connected to a 60-meter line of 60-meter red line, and it has a sampler, a DNA sampler that touches the surface of the leaves. Or we can also extract water filtration, and then this DNA that gets stuck on this wet tissue basically gets transported back into the field and can then be analyzed and sequenced. So these are these drone-based approaches of sampling that are more and more using machine learning to be controlled. One really exciting part of using machine learning that is coming up are bioacoustic sensors. Bioacoustic sensors, and I have started my talk a lot with these sounds of the forest, right, are quite cheap sensors, relatively low price. This is an audiomorph sensor. It's the size of like a small cigarette pack, basically. It can record 24/7 for 2 weeks with just 3 AA batteries. And it provides you kind of a spectrum of all the sounds that are in the forest. So you can see on the bottom right, this is a visualization of the soundscape. This is how you read it, is basically the y-axis is the frequency of what is recorded in kilohertz, while the x-axis is the time of it, right? And one of the most beautiful things about nature is it's somehow learned, all the species, all the animals have learned to be like radios, you know, like the birds are usually in between 1.5 to 5 kilohertz, right? And they usually don't overlap each other with their songs, while insects are more above 5 kilohertz. So they learned how to basically occupy different kind of channels of frequencies, basically like a radio sender. And this is something machine learning can use to predict, for example, what kind of species this is. So here, for example, this is using a transformer on the visual spectrogram of the audio to classify potentially what kind of bird song this is. As you can see, these kind of small things here, these are bird songs, and bird songs have a very unique pattern depending on what kind of song from what a bird it is, and this is a uniquely suitable task for machine learning, given that there is labeled data, which is always the problem here. So finding out labeled data, having someone listening to bird sounds, marking this in the spectrum, and training the machine model is one of the big challenges here. So last quiz for today. We have 4 different kind of sounds. So now we have to be really silent to listen to all of them. And I want you to basically tell me which of these, I don't know what the quiz is, maybe it's correct, but like we have 4 different kind of categories: natural forest, then we have a reference forest, we have a regenerated forest, we have a pasture, and we have a plantation. And listen to all these 4 sounds, and then the next quiz would be what of these sounds relates to what of the forest. So let's start with A. This is B. So
Can you increase the tone volume, please?
I don't think so, unfortunately. Should I try to see if I can share it one more time with sounds? Let me try, because it didn't work when I was trying to share it, unfortunately. It's somehow blocked. Unfortunately not. So I'll just try to be very silent. So this is C. You can hear the difference between A and C, for example. And lastly, that's D. Oh, so quiz. Can you start the quiz? What is oh, A, B, C, D. Okay. I don't think it has. It's just choosing A, B, C, or D. Okay, this is a, I think, miswritten quiz, but no problem, because like there's no A, B, C, or D. You basically have to guess what is what. But let me just reveal then what it is, because I think it's pretty interesting. So the first one is a reference forest, a very natural forest, healthy, the one that I played in the very first time. Oh, and then the next one, that's when you naturally regenerate the forest. So it was deforested and regenerated. And that compared to a plantation. This is something we just listened before. You can hear the difference. Like it's much less birds and much less biodiversity. And then lastly, the pasture. This is where the cattle are raised. And in fact, one of the beautiful parts of this is that bioacoustic sensors can provide something what we call a soundscape. So we have landscapes where we look at, for example, how forests and trees look like, but we also have soundscapes. And soundscapes are, you don't have to know what species this is. We can hear it. We can hear the difference between a natural forest, and we can hear the difference between a forest that is deforested, like a plantation or like a pasture, right? In fact, you can also visualize it. So I mentioned briefly, there different kind of animals are coming with different kind of frequency bins. This is the visualization of 24/7 of recording, so like a clock. And you can see, for example, green, these are birds. birds and insects that are happening between 1,500 to 5,000. They're active during the day. And there's a special big peak at 6 a.m. This is when the sun rises and everyone gets crazy. You can measure that intensity of sounds that are coming up. And then in the evening at night, you can see how the color shifts towards higher frequencies. That is because now the frogs are active and the bats are active. And this is basically showing how this evolves over the day. On the other hand, you have another graph, and this is in a city where you don't have these very clear color distinctions. It's kind of like all mixed up. And also the amplitude is much smaller, and it gives you a signal of what you heard about the pasture and the natural forest. Gives you a signature of how healthy, how structured that forest is. But you can still see and recognize the sunset at 6 p.m. where a lot of activity is happening, and slightly also at 6 a.m. the sunrise. So I just briefly now mentioned very, very quickly all these sensors, but I want to spend my last 10 minutes on briefly the limits of AI and also the role of indigenous people and local communities and frontier data and how important this is towards protecting forests. So very famous picture, Joy from the Algorithmic Justice League, back then a PhD student at MIT Media Lab. She showed that back then existing face recognition algorithms were not able to detect her face. But the moment she was wearing a white mask, it worked. So our data is biased. And that is a problem because algorithms can amplify these existing systematic biases. The reason why these face algorithms didn't work on her face is because there were not a lot of data, and it still is not. That is, and you have way more data from a certain kind of test point than you have from others, and that creates biases, and also the efficiency of the algorithm is unfair. Another very famous bias is here a diffusion algorithm, that a Gen AI algorithm actually that takes a picture of Obama, depixelates it, and then yeah, it's definitely not Obama. The same problem with the bias, basically having a lot of data from one place, but not a lot of data from the other place. We have the same problem with biodiversity and nature data and forest data. This is basically how the world would look like if we just plot all the nature data out there. This is how you can see the more red the color is, the more actual biodiversity is in this place. And the more darker is, there's not a lot of biodiversity, but we have humongous data, overlapping data in the US and Europe and China. But the places where we should have a lot of data when it comes to nature, because that's where nature is the most, Brazil, Congo, Central Africa, Indonesia, we have very few data sets. So one really crucial example where we can see this is, for example, in Ecuador, we measured every single tree in small landowner sites. And so we know exactly the carbon that is stored in this small area. And then if you compare this, for example, with back then satellite-based data, Global Forest Watch had a biomass layer that they released. We can see that many of these layers are overestimating these small areas in the global south, up to a factor of 10 overestimation. And you can imagine how critical this becomes when decision makers want to use the algorithms to, for example, give out carbon credits, right? So that's why it's really important to have field-based data, calibrated field-based data, involve local communities and indigenous people when it comes to designing these AI algorithms to be less biased. And that's the last section for today. Talking briefly about the critical role of IPLCs, indigenous people and local communities, when it comes to co-designing AI for nature and forests. So, lessons first, they need to be involved in co-design because of all the things I just mentioned about the bias, about the potential danger, the unfairness, and also because oftentimes they are the main beneficiaries of these algorithms, right? They are the ones who are at the front line living in these communities. So having them involved basically ensures that you're building something that is not just built without them being used, right? Like you need to build it together. Also, so one thing that I learned during my work with the local communities is that culture plays a really important role when it comes to how land use and land systems are changed. And AI provides us with a really great opportunity nowadays to kind of measure this. In the past, we had only surveys to measure that. Surveys are really difficult to scale. And so one of the ways we at Gainforce currently are deploying generative AI is to create a chatbot that is based upon one of our observations that local communities love to share stories. That's how they naturally share knowledge among each other. They don't come in with a form and fill like blank text. They basically tell a story. And in the previous past, this unstructured data was really hard to leverage and structure and make sense of it. But using generative AI, for example, we built a small Telegram bot. Telegram is one of the most used apps in all of Brazil. That's why we decided to use that, where you can share a picture. And then this Gen AI is imitating a very curious niece to respectfully ask more follow-up questions. And one of the really beautiful things about the current trends of AI models is they can be way more inclusive. Oftentimes, English is a very limiting factor when it comes to providing information. But these generative AI algorithms now, these chatbots are able to speak in many languages. Portuguese here, for example, is the critical language that you can just speak into naturally, and it can store this information. We tested this out with indigenous communities all around Manaus to leverage potentially storing oral history information, of course, with their consent in a capacity building workshop. And that's also things that we learned, that when you work with them, you need to first start trusting, like just building trust, not just through explaining and capacity building the technology. So you're basically teaching them how it's used, but also ensuring that they are owning the data itself. One of the most common concerns working with local community members is who owns the data. Oftentimes, what we see nowadays, we work with a lot of local communities. We hear the same old story. Someone from the global north came, collected data, and never returned saying what it was used, never shared any of the benefits. It's kind of a modern day of data colonialism. And many of these communities are aware of this. So you really need to build trust through teaching and knowledge sharing. But then as a second step, you need to, when you design these algorithms, you need to build trust through data sovereignty, ensuring that they own the data, they can run it on their databases and manage the data and host it as well. And lastly, another important step is trust through ownership itself. So once they are being taught, once they know how to manage the data, and once they have built the capacity, you have to give kind of the torch to the next one. Here, Marina from our team, she's been teaching this technology now independently from her community to the next community without our involvement. And this is how trust is basically spread through the communities. These generative AI algorithms are really great in really integrating local community knowledge. One of the things we're using is RAG. So once you consented on this information, you can use a user query to query that IPLC knowledge and ensure that it's mixed together in an LLM, and you can provide more context. For example, you have a species name of a plant, then you have medicinal information. You can ask this and it will enrich this, for example. IPLC knowledge is also really amazing when it comes to sampling. Here, for example, we have audio morph sensors that we given to many communities around Brazil for them to install. And many of these communities know exactly the right place where to install these sensors, right? If you come as a foreigner, as a gringo, and you want to install these sensors, you have a much worse prior on locations than the communities. So you can use this knowledge, you can work together with them to have good priors when it comes to sampling locations. Another really cool example I found is few-shot learning, few-shot examples. IPLC knowledge oftentimes, especially for really valuable economical trees, they know the locations of that. If you align this with a different kind of data modality, here, for example, high-resolution satellite image, you can see that the Brazil nut, for example, a really important tree for these communities because it provides financial income and food, and it can only grow in the natural forest. You can see them from space. At least you can see these patterns of big trees. They have humongous trees that stick out of the canopy and they throw a shadow. And these kind of locations are well known among the communities. These Brazil nuts come in groves. So you can train a few-shot learning algorithm. So you self-supervise using a geospatial foundation model, but then you can train a few-shot learning algorithm to predict the likelihood locations of these Brazil nuts, basically. lastly, really, really important, co-designed AI needs to, especially when you're like incorporating indigenous knowledge and local community information, it needs to be connected to shared benefits. So we need to make sure that once these algorithms are developed, for example, once you have the capacity building done and finished, and potentially also the data collection is led by the indigenous people, the benefits of these algorithms need to be either through a contract, through an agreement, needs to go back to the communities. This is really, really critical to not lose the trust that you took so long to build. And also, this is the way forward to include them into the design, but also make sure that the benefits also flow back to the community. So lastly, I want to share like a small video of how the communities have been using Kerner, the chatbot application. And I'm always really fascinated about how excited they get when they see it.
Essa ferramenta ela é importante porque, por exemplo, os conhecimentos indígenas ainda estão dentro da questão da oralidade. Então, eu acho que essa inteligência artificial ela pode ser utilizada para resguardar esse conhecimento, né? Porque é uma plataforma que vai armazenar esses saberes e colocar isso, né, para a sociedade, para o mundo.
Essa abordagem mais humanizada valoriza o conhecimento individual mesmo. Cada pessoa sentiu até que a AI estava emocionada com as histórias que ela contava.
É algo muito incrível, né? Porque a gente descreve um pouco da imagem que a gente está inserindo na plataforma e ela vem com muita curiosidade sobre o que a gente está dizendo e vai instigando a gente a falar cada vez mais aprofundado, como se fosse outra pessoa do outro lado falando sobre um determinado assunto.
Então, a nossa proposta é continuar trabalhando próximo do Parque das Tribos e todas as comunidades indígenas que toparem a adotar essa inteligência artificial, que está agora num bot no Telegram, então está disponível para o celular de qualquer pessoa, e é simplesmente mandar uma foto e gravar um áudio e aí começar a conversar.
And lastly, I just want to share this kind of clip. So lastly, I want to quickly go through the lessons learned. Really important. When you design these algorithms, they need to be transparent and open. Again, these MRV algorithms are key building points of policy and decision making. So you need to be transparent. You need to make sure that it's clear how this data was trained, and you need to make sure, you need to understand that it might influence policy, and therefore it can create dangerous feedback loops if you're not aware of biased data sets, for example. It also needs to be co-designed with local communities, data ownership again, make sure that the specific metrics that you measure success or the loss of these algorithms is discussed with the communities, because oftentimes when you have certain kind of measurement that comes to target, it ceases to be good measurement. So working closely in feedback loops with the communities is really important to make sure that you don't have the first problem. And then the benefit sharing, right? So we talk a lot, when we talk about data, we talk a lot about these FAIR principles: findable, accessible, interoperable, and reusable, making these data sets free and findable. But they oftentimes stand in contradiction to CARE, which is the benefit sharing, which is making sure, okay, these data sets, sure, they are fair, they are maybe open for the scientific community, but somehow someone needs to pay for the collection of data sets, because this is work. It's oftentimes very dangerous work, and it's a matter of respect. So these two things need to be aligned. Oftentimes it doesn't have to be a payment, a financial transaction. One of the things I learned is that non-monetary benefits sharing, like knowledge, is equally important as a transactional one as well. And lastly, just a 30-second teaser of one of the communities who work together in Manaus, and just the feeling I have whenever I return to them. I think this video captures it quite well. And with that, I will close my talk. So thank you so much so I will skip this video because I want to have sure we have a little bit more time. Thank you so much for your attention. And yeah, if there are more questions, let me know.
Okay, yeah. Thank you so much, Dr. David, for the insightful session. I've learned a lot, and I'm very sure our participants have learned a lot as well. So there are lots of questions, but you'll be answering few while we'll provide feedback to others on our community platform. So I'll be reading out the questions. So the first question here, there has been much controversy about the issuance of carbon credits from avoided deforestation. There are studies that indicate that the results are overestimated. Can AI support more accurate estimates for the issuance of carbon credits?
The answer is yes and no. So this is actually one of the questions I think I put even in the multiple choice afterwards. But the problem is really here, yes, in a sense, it can automate lots of tedious work. But also no, because oftentimes, depending on what your algorithm is, if it's, for example, only satellite based, I highly doubt it. Because remember, the satellite cannot tell you why A, B, or C. Remember the quiz on the second quiz? Which one of this is actually more likely to be cut? You need to have more information. You need to have land use information. Oftentimes, you need to know the realities on the ground, right? So you need to work again with IPLCs. So it really depends on how you define this algorithm. I do think, so my hypothesis here is AI is not a silver bullet. It will not solve the trust in the carbon credit market, but it can be a tool that can accelerate trust when designed and co-developed. That makes sense.
Yeah, thank you so much for the answer. Here's another question. Is it possible to use machine learning to understand what areas are more at risk of deforestation? What kind of variable can we use for a data-driven model?
Sorry, so the question is, okay, which one is more at risk?
Is it possible to use machine learning to understand what areas are more at risk of deforestation? Then what kind of variables can we use for a data-driven model?
Yeah, I do think so. So again, with the hindsight of making sure that these algorithms are well developed, but they're very strong predictors, like a road, like the river, like is it at the forest edge, right? That will, if there's no additional thing, like no land, like it's not happened to be a protected area suddenly, but like everything is the same, but this one area is much closer to the road than the other one, then yes, that's a higher risk. But again, oftentimes it's really hard to say, just based on the site data again, because you're missing the big picture. But these are kind of variables that people would use, like human pressure, infrastructure, closeness to the deforestation border, and the past spread of deforestation.
Yes, thank you very much. There's another question. Are there any machine learning Python libraries for soundscape?
I actually don't know. No, I don't think so. It's very new. So I'm sure when you go to GitHub and you Google it, you will find some, but there's not a big PyTorch one, I think, that is specifically for soundscapes. I think many people have built their own kind of models. There's, of course, like existing models, like the one that I just showed you. For the bird detection is an AST, like an audio spectrogram transformer. The Hugging Face has an implementation of that, but there's no library that specifically focuses on that, unfortunately.
And the last question, one of our participants is asking that you provide more information on the sensor that is attached on your drone for airborne DNA sampling.
Yes. So the sensors are a sheet of paper. So it's just a wet paper that touches the leaves. This is how you surface sample. It's kind of like you can also put a cotton cloud or something that just captures DNA, right? Like, and then another sensor, it's not a sensor, it's a machine. It just filtrates water. So there's a filter that captures DNA particles, and then you can filtrate water through. So this is another sensor that we install underneath the drone.
I have a small announcements to make. Please fill out the feedback form, what I several times now I posted in the chat, so that we have that. Thank you. Yeah, please.
Yes. Thank you so much for the session today. Thank you so much to our participants for staying up until very last end of today's session. We had an insightful conversation around artificial intelligence for agriculture, where we discussed so many things, the factors affecting the implementation of artificial intelligence in agriculture. And we also have an insightful conversation by Dr. David, where we explored the application of artificial intelligence for forestry as well. So we've come to the end of our session for today. If you have any other questions, you can do well to post on our community platform, where we'll do our possible best to provide response to all your concerns. Do enjoy the remaining parts of your day. Thank you. Goodbye.
Thank you so much. Goodbye.